I'd like to show an example of how we can incorporate both work and heat into problem solving around internal energy. So remember, our change in energy for our system is that it will be equal to the heat transferred plus the work done. Uh, to the system. And so that work is equal to the negative of our pressure times the change in volume. And pressure times volume is equal to the number of moles times the ideal gas constant times temperature. And so that ideal gas constant, if you haven't yet reviewed gas laws, is something that will be discussed in detail in when we do gas behavior. And if you're familiar with it, then this is our kind of basic equation for determining different properties of gases from other properties that we can measure about it. And so again, what we're looking at with our work is that pressure and that volume work. So what we're going to do is assume for this reaction where we have copper to or we have copper oxide and oxygen combining to form copper oxide, is we're going to take a look at what the change in energy would be, the internal energy. And we're going to know a little bit of information. We're going to know that the heat transferred is negative 75.64 kilojoules, and we'll know that the pressure of the system is 0.9869 atmospheres. And the temperature is equal to 25 degrees Celsius. And in Kelvin, that'd be 298. And we're looking at 0.259 moles reacting. And so what we're going to do is need to know what our pressure and our volume is to calculate work. We already know what Q is. So we have Q right here. And we need to know what work is to be able to calculate our change in internal energy. And we already have our pressure, but what we need is our volume. And so rearranging the ideal gas law, our volume will be equal to the number of moles times the ideal gas constant times temperature divided by pressure. And so we'll solve for that volume right now for this number of moles. And this is the number of moles of oxygen consumed. And what will happen here is the oxygen will be consumed in the reaction, so it will become part of that copper oxide in the product, and so it will decrease. So we're going to see our volume decrease as that oxygen is consumed. So let's figure out what that volume of oxygen is that participates in this reaction. So volume is going to be equal to that 0.259 moles. Our ideal gas law constant is 0.0821 liters times atmospheres divided by moles Kelvin. Multiplied by our temperature of 298 Kelvin, the temperature the gas is at, all divided by that pressure, which is 0.9869 atmospheres. Plugging that into our calculator, we're going to get a value for volume that is 6.42 liters. So that means that this is the volume that the system will decrease by. Another way to think about this is the initial volume, and my final volume is going to be equal to 0 liters, right? So I can calculate that change in volume as my final minus my initial. And so that would be 0 minus 6.42 liters, or a negative 6.42 liters. So now I can go ahead and plug that value in up here into my work expression. And so work is going to be equal to the negative of my pressure times the change in volume. So that'll be the negative of 0.9869 atmospheres times that change in volume, negative 6.42 liters. And plugging that in, I am going to get a value that is about negative 0.65, I believe. So plugging these values into my calculator, I'm going to get 6.335, and my units here are liters times atmospheres. So now I'm ready to start thinking about my internal energy. So I'm going to bring this down here. So my heat is that negative 75.64 kilojoules. So I'm gonna plug that in here. Now I need to plug in work. However, I have work represented in units of liters times atmospheres. So I really need to keep my units the same if I'm adding them together. So I need to convert this into kilojoules. And there's a handy equation, or sorry, conversion factor for that, which is that 101.3 joules equals 1 liter times atmosphere. So we can utilize that. So we're going to see our 6.3 35 liters times atmospheres multiplied. Here, I'm going to make a little bit more space here by 101.3 joules divided by that 1 liter atmosphere. And then I'm going to do a joule to kilojoule conversion to make sure my units are the same. So that'll be times 1 kilojoule divided by 1,000 joules. And that'll give me a value that is 0.642 kilojoules. So now I'm going to plug this value in for my work. Um, and so my change in internal energy will be that negative 75.64 kilojoules plus my 0.642 kilojoules from my work, giving me a change in internal energy that's negative 75.00 kilojoules. And so we can expect an exothermic style reaction here. And I think it's worth noting, like, it's the work is a small contribution to this reaction, and that work that's done, that pressure volume work, will never be super huge relative to heat typically. And so a lot of times chemists will just ignore the work and focus on the heats that's transferred as it's kind of the main component of this change in internal energy.